I could present here, I decided to kind of encompass what I've been doing at Syngenta. I've just finished last Friday, and within that I've been in the Department of Product Safety, particularly looking at environmental risk assessment, which Neil kind of touched on in his talk yesterday. So firstly, I'd like to give you a little bit of a background on pesticides and how they're transported and what we already know. There are hundreds of approved active ingredients in the EU. One thing to note, I will keep on saying EU. In a post-Brexit world, we're assuming it's very much the same. As of current, a lot of the legislation is very similar, but may divert in the future. It's also very different to American approval systems. So yeah, I will keep on saying the EU, but that's just probably from my time in Syngenta, where I focused on EU legislation. So this is a map. I found a nice one in Nature Geoscience a few months ago, just highlighting the diversity of the number of active ingredients that may pose a risk to the environment. When we're undergoing pesticide risk assessments, we split it into 3 categories. The first is the ecotoxicological safety, the consumer and operator safety, including dietary, and thirdly, environmental safety. Within environmental safety, there are 3 aspects: air, soil, and water. And so surprise, surprise, I today will be looking at air. So what does the regulation say? The regulations say that lifetime in the atmosphere must not exceed 2 days. So this prevents the possibility of long-range transport. I also will highlight, for example, water. And in water, it states that groundwater must be maintained as a pristine environment. So all the regulation is quite conservative these days, and it hopes to protect the environment. So when we apply a pesticide to the environment, a number of mechanisms shown here are possible. And as I said before, our main transport route today will be looking at the air, particularly quite short range transport. I won't go into too much detail about the rest of the stuff, but it's a nice picture to look at. So how does a pesticide reach the atmosphere? We have a lovely tractor here spraying some pesticides onto a field, and one of the main routes while spraying is occurring is this spray volatilization. So this is the spray that does not end up on the crop or the soil, and often can be transported short distances. Might reach a local town, might reach a local bystander, might get into some water in nearby ditches, that sort of thing. And then the 2 other is plant and soil volatilization. The majority of this can occur hours, weeks, months after application, depending on the active ingredient. Going the wrong way around. So today I'd like to, I sort of touched on saying that I'd like to almost get into that environmental risk assessment. So the first thing that's actually considered when we look at the air risk assessment is its volatility, with the main indicator being vapor pressure. So what do we know about vapor pressure and what are the guidelines? This is in the EU once again with Focus, a group that came up with this, suggests that the low or non-volatile, no further assessment is required, as it's assumed that it's not volatile in the air, and volatile is not likely to be in the atmosphere. So just remember that for the future. So to measure volatility, there's 3 main aspects that I have sort of considered. The first value is the regulatory literal value. This is stored normally in the renewal assessment report, so a very sort of legal government sort of report that will decide whether that pesticide can be renewed for the next 10 years. It is measured according to a standard method. However, I like to sort of question that standard method, mainly because a lot of the time they are not measured at the temperature that is relevant. So it's often extrapolated from, say, 50 degrees to 25 degrees. The other method is through the EPI suite. So this is an American tool which gives ideas of a range of compounds using structure-activity relationships. One thing to take into account that it isn't necessarily accurate, it's just that first step that is often used to try and predict what a compound may do in the environment. The third and the more practical version is using the Figueroa-Sims here, and that is the technique I use in Manchester, and I'll go into a little bit more detail about that. But if you'd like to know more, I don't really have enough time to go way deep into it, but often people get a little bit stuck on that and a little bit confused, and I'm sorry that I haven't been able to have time to fully explain it. So, as I said before, this is the SIMS, so it's a chemical ionization mass spectrometer using an iodide adduct ion, and it is coupled with a Figueroa. So the Figueroa is the filter inlet gases for gases and aerosols. The Figueroa enables simultaneously sample of gases and aerosols. So what happens here is we sample the gas phase in this inlet and the aerosol phase in this. The aerosol phase is collected in a filter here, and when it is moved into the aerosol phase mode, the heating block is heated to 300 degrees, and the idea is that we can infer volatility as the temperature increases, the compounds that are on the filter volatilize off. So this is some general Figueroa data where we infer vapor pressure from the Tmax. This is the temperature at which the maximum ion count occurs, and we use this equation where A and B are inferred from calibration experiments. And I've been doing a lot of calibration experiments while I've been in Manchester, often with these acids. So finally, to some data. On the bottom is a number of active ingredients, pesticides, all of which but one are on the market. And I have, from that focus report, decided to put the red lines of where that is seen. I'm going to focus on two different pesticides today. The first one is mesotrione. This is a Syngenta active ingredient, and the second one is trifluorine, which is not. Mesotrione is interesting because this is the literature value, but the value that I've measured using the SIMS is much lower. So that would consider it as low or non-volatile. Whilst on the other hand, trifluorine is completely different and is seen as quite volatile by all three of these methods. From this, with mesotrione, we've seen that it's a value of less than 10 to the minus 6, and focus would predict with no potential volatility, so no further risk assessment is required for mesotrione. Also to note as well, when I was able to go to Syngenta and learn more about the renewal process, the value of the literature was actually seen as less than 1. So it was quoted in the literature as 1 to the 10 to the minus 6, which is something that I'd missed before. So suggesting that the value here is actually that and below. Therefore, we're not worrying about it being in the atmosphere. Trifluorine, on the other hand, is a completely different story, and something during the renewal process that would occur, would further studies would need to undergo to ensure that no environmental or toxicological impact would occur. Just a little bit about trifluorine, as we're going a little bit into it. It's a pre-emergence herbicide to control grasses and broadleaf weeds. When I mean pre-emergence, this is often sprayed on bare soil, post-harvest or pre-planting to get rid of any weeds present. Spoiler alert, it was banned in 2008, but it is still used in the US. And the reason for its banning was due to its high toxicity to marine environments. During my placement, I looked at a number of active ingredients from data in France. So this is total data across many sites in France. France have a brilliant monitoring network for pesticides, and it was really actually interesting to get really delved into the data. One thing to note with this plot is that it is in log scale, and after 2008, it does dramatically decrease. But we are seeing some of it. This could be through other uses that are not banned or even emergency authorizations. This is a graphical reason of the previous data. And as you can see, that trifluorine has been seen all over France from the years 2002 to 2021. So next, I thought I'd go into more and put into my chamber studies that I've been doing in Manchester. And trifluorine was one of the active ingredients that I looked at. So this is the chamber in Manchester. It is basically a big plastic bag, and we were able to sample from it, able to turn lights on from it. It's controlled through air conditioning to control the temperature and humidity. And what we do is we nebulize the pesticide into there. We can measure the particle sizes using the SNPS. And also the chemical ionization mass spectrometer that I spoke about before. We also analyze through that. We start off in the dark conditions. We turn the lights on that has been characterized to a third of the concentration of the OH in a typical Manchester sunny June day. That's how it's described in the literature. So results. The top and the bottom is the same experiment I will tell you about. The top is just showing the active ingredients trifluorine, whilst the bottom is trifluorine and its oxidation products. So what we do, we start to inject. We stop the injection, we turn some lights on, and we turn some stronger lights on. One thing to note as well is we've done this in the Figaro mode. So here, this is seen in the gaseous phase, and then it hasn't disappeared. What we've done, we've moved into the Figaro of the heating, and the trifluorine isn't in the particle phase at this point. It's very volatile. It's not expected to be in the particle phase. However, some of the products that we've observed have. So this actually is interesting because we might be able to infer some volatility of these products. And looking at the major pathways, here they are. We've got a H abstraction pathway and an OH addition pathway. So these two major pathways have been identified from previous literature of trifluorine and the observations I've seen in the chamber using the mass spectrometer. I'm now going to compare. The next slide is what the renewal assessment report for trifluorine when it was actually banned said about the trifluorine in the air. And they used the EPI suite that I talked about previously. I've included the rest of the active ingredients that I said before, just for context, but mainly we're looking at trifluorine at the end. As we can see, it reacts very quickly, which is good for us in the chamber because we're able to get quick monitoring of products. But as you notice, the EPI suite predicts just the H abstraction pathway and not the OH oxidation. So it does suggest that we do have some disparity compared to what they've used before. So overall, with trifluorine, we've seen it's very volatile. And this would mean that it's rapid photodegradation to breakdown products and no major long-range air transport is expected. So we conclude here in the air risk assessment that it wouldn't be an issue. However, you must consider trifluorine as a whole and not just air. The high toxicity of the compound results in a small chance that spray drift could lead to exposure to aquatic organisms, which is very harmful too. And thank you for listening.